second that you collectively pulling my leg by not typing anything there. I thought I was talking to myself. Okay, never mind. So thank you very much. Thank you very much. Okay, so it's time for us to move on. So we are done with. Okay. It's time to move on. We are done with chapter 2 and the time response of control system. Today we are going to talk about the stability of a linear control system. When we construct a feedback control system, you cannot run away from the problem of stability. So, okay, so I can hear some echo there. You need to switch off your microphone so that we don't hear any background noise. Where was I? Look at the first sentence there. How stupid is that? See, closed loop feedback system is either stable or unstable. Who the hell make that statement? Of course, it's either stable or it's not. It's either stable or unstable. So when we categorize stability in that way, we say it can be either stable or unstable. This type of characterization is referred to as absolute stability. Okay, it's either we just want to know whether the system is stable or not. But before that, let us go back to concept of stability. What do we mean by a stable system? See, the definition of stable system is stated there. A stable system is defined as system with bounded response to a bounded input. When the response of the system is unbounded, it's getting bigger and bigger and bigger, and we say that is an unstable system. But here's an example. When we develop or construct a closed loop feedback system, we are not going to be able to run away from the problem of stability. A stable open loop system can become unstable if we don't design the controller properly. For example, if you make overcorrection, I'm not sure the kids today, so some of you might be familiar with riding a motorcycle. Some of you may have accident already riding a motorcycle. You see, sometimes you make a correction. You see, when you ride a motorcycle, suddenly you see, for example, you see a cat in front of you, and then you make a correction to the left. So your motorcycle will go to the left. But imagine that you make a larger correction than necessary. Then suddenly you say, "Oh, I'm going too much left," and then suddenly, okay, you say you have to make a correction again to the right this time. But again, when you make an overcorrection to the right, and this time it's going to be even a bigger correction to the right. You go even more to the right this time, and then you make a bigger correction to the left again, and suddenly you found yourself in the drain. That's what we say when we say that the system is unstable. The response is unbounded. It's getting bigger and bigger and bigger. For example, here. Where is this? Why is it everything is there? What's going on? But the input, okay, imagine this is the system, the input must be bounded first. Of course, when the input is unbounded, then we can expect that the output is unbounded as well. So this is some of the typical input that might be imposed on a system. It can be an impulse, a step, and some traction input. The first two examples here, this is a stable system, and oscillation does not mean that the system is unstable. It is just oscillation. Increasing and then decreasing back also still a characteristic of a stable system. Only when the response, the output is getting bigger and bigger and bigger and bigger and suddenly very big. That is what we mean by the system become unstable. So what exactly made the system become unstable? What is it? What is it that made the system become unstable? I forget about that. Let's take a look at this example 3 and example 3.1 and example 3.2. So we have this system. What's going on? What's going on with my screen? Something's what's going on with my screen today? What's going on with my screen? What the hell?
Not sure, Doctor.
Someone chanting your screen. It's vandalism. Yeah, I know that. What the hell is going on with my screen today? Okay, never mind. So okay, so we were discussing what make the system become stable or unstable, mathematically speaking. So why my computer is so slow today? Probably it's about time for me to get a new one. Yes. All right. So look at example 3.1. So he says here, obtain the time response of the system shown below for a unit step input. Determine whether the system is stable or not. So when the system is subjected to a unit step input, does this system stable or not? This is very simple question. Oh, by the way, I don't play games. I'm just an old man already. By the way, today I'm back in my office, so I can write something on the board today. But what the hell is going on with my screen today? I don't know. There's something.
Mana aku tekan ni? Aduh, jatuh. Sorry, aku nak set ni.
Asal kacau live tu.
All right, so that's example 1. We have example 1. So the system is 1 divided by s plus 1. So the output is u of s multiplied by that. But since we have this unit step input is in Laplace transformation format is just 1 over s. Okay, so then t. So now this is the response to a unit step input. And then if you draw the function there, it's just exponential function. See, the critical here is the minus sign here, e raised to the power of negative t. So that is going to be, as t approach infinity, that's going to approach 0. So your final value is equal to 1. Yeah. Why don't you just everybody just sing, and then we can have some fun here. So we say that this system is now is stable. Stable meaning that the output is bounded. It does not get very large. It doesn't get infinitely large. So this is a stable system. For a unit step input, which is a bounded input, and then our output is some exponential function that finally approach the value of 1. So we say that this is a stable system. And of course, as you can tell already, the second example by default is going to be unstable. Otherwise, why we are doing this? Example 3.2. Now obtain the time response of the system shown below for a unit step input. I'm just going to write example 2. Y of s is equal to x1 s. This is minus. Oh, sorry. Let's go to the whiteboard. Okay, so that's example 2. And then for a unit step input, then you perform the partial fraction. Then you have that. So you start at what? Start at 0. And then if you draw the response, okay. See, because this is e raised to the power of positive t, as t approach infinity, so that is going to be infinitely large compared to -1. So it's going to increase. So this is what we mean by unstable system. So what exactly makes the system unstable mathematically? So you can see that the system becomes unstable if only one of the term approach infinity depends on the sign of the roots of the denominator here. So if you have a positive root, then the system is going to be unstable. Here you have a -1, but in the second example, so the root is +1. The roots of the denominator of your transfer function. So if you have one positive root, then your system will become unstable. So you can generalize that by stating that okay, so stating here that where is it? Oh, okay, the discussion will come in later. So the sign of the roots of the transfer function will determine whether the system becomes stable or unstable. So we will be looking for a positive root. If there exists a positive root of the denominator, and then we can safely say that the system become unstable. So in general, we can discuss in general term what stability means. Now, if we look at the closed loop system, we're going to have this forward transfer function gh of s and the feedback transfer function h of s. So when we obtain the overall transfer function, we have this g divided by 1 plus gh. So the equation 1 plus gh is known as the characteristic equation. See, the denominator of the transfer function equal to 0 is known as the characteristic equation. This equation will characterize whether the system is stable or not. So the roots of this characteristic equation will determine whether the system is stable or not. If there exists one positive root, then the system becomes unstable. Only one is enough to make the system become unstable. We want all the roots to become negative. For example, here, if you write the equation in zero pole format, so this is known as zero pole format. Z plus S, S plus Z1, S plus Z2, there's a numerator. The numerator will not determine whether the system is stable or not. Only the denominator of the transfer function that will determine whether the system is stable or not. If there exists one positive root, then you can safely say that the system is now become unstable. Only one term that will go to infinity is enough to make the system become unstable. But sometimes the roots are complex. It is not just a distinct real number. When the roots are complex number, then we are looking at the real part of the roots. If there exists a positive part of the roots, then we say that the system is unstable. So we can see the region for stable system and the region for unstable system. Where is it? There. On complex plane, so if you plot all the roots of the characteristic equation, okay, but by the way, what is the roots of an equation? For example, a quadratic equation, ax squared plus bx plus c equals 0. So the roots are the value of x that will make the equation equal 0. If you have a quadratic system, then you're going to have 2 roots. If you have a third order polynomial, then you're going to have 3 roots. For a stable system, you want all roots to be on the left-hand side of the imaginary axis. You're going to have some real roots on the real axis, and you're going to have some complex conjugate roots. As long as the roots lies on the left of imaginary axis, then we say that the system is stable. We need all roots to be on the left-hand side of the imaginary axis. Sometimes the root, we say the root, sometimes we say it's the pole. Sometimes we use the term pole and roots interchangeably. See, all poles of the closed loop transfer function must have a negative real value, meaning that all poles, sometimes people use poles interchangeably with the roots. The control engineering people like to use the word poles. The mathematician use the word roots. As long as all poles lies on the left of imaginary axis, then we say the system is stable. So this is called a complex plane, an S-plane. If one root lies on the right of imaginary axis, on the S-plane here, and we say that the system is unstable. One root lies on the imaginary axis on the S-plane, then we say that the system is stable. All poles, for a stable system, all poles must be on the left of the plane. This is called the S-plane of a complex number. I can still remember the joke my professor, my lecturer, when he talked about this stability of closed loop system, probably 35 years ago, I think. I still remember the joke until today. Now I'm passing the joke to you, so that in the future you can tell your children about this joke. So he said that one day he was flying flying in a plane. See, you can see where the joke is going already, right? So this is the plane, the complex plane, imaginary axis, a real axis. It must be to the left of the imaginary axis. And then he said he was flying in a plane over an Atlantic Ocean, and suddenly the plane hit a turbulence, so it becomes slightly unstable. And then he said that, okay, the captain make an announcement. Hello, this is your captain speaking. All poles, please. Okay, we are experiencing some turbulence that making our plane unstable. So to stabilize the plane, please all poles move to the left of the plane. Did you get the joke? No? See, the Polish people, we call that pole. So the captain wants the poles to move, all the Polish people move to the left of the plane so that the plane becomes stable. Forget about it. You never get my joke anyway. All right, okay. So we want all the poles to be on the left of the imaginary axis. Now let's take a look at this. Example 3.3. Determine the stability of the system with characteristic equation given below. So this is the characteristic equation. Characteristic equation is the denominator of the overall transfer function. Only the denominator of the overall transfer function will determine whether the system is stable or not. All you have to do is find the roots. If one of the roots are positive or has positive real part, then we know that the system is unstable. So this is a third order. You're going to have 3 roots. Let me go back to my whiteboard. Okay. So, okay, this is now a third order polynomial. So we can factor one of the roots at -2. And then since this is a third order, then we're going to have three roots. One is the real root, which is -2, and the other one is -1 plus n minus j. So we see that. So this is all the three roots. The one that I marked by x. So those are the three roots. So or the poles. So since the roots or the poles lie on the left of imaginary axis, and then we say that the system is stable. So a third order system is going to have three poles or three roots. As long as all the roots lies on the left-hand side of the imaginary axis, then we say that the system is stable. Let's go on to the next question. And then you need to do this for every single system. So finding the roots of higher order polynomial, it is not that easy. Even a third order polynomial is not easy for you to find the roots unless you have a very good calculator. Then you can just plug in the equation and the calculator will give you the roots for you. There's always a trick for that. Now let's take a look at next question. .4. Right. For a marginally stable open loop system below, determine the stability of the closed loop system if the proportional controller gain Kp is equal to 24 is used. Now, it is given that this is an open loop system. It says that open loop system is marginally stable. Marginally stable because one of the roots is 0. See, your roots are -1, -2, which is on the left of imaginary axis, but one of the root is 0. It's exactly on imaginary axis. So that is why this is a marginally stable open loop system. And smart Alex come in here and say, okay, since this is a marginally stable system, let us use a proportional controller gain Kp, turn this into a closed loop system and see whether the system is stable or not. Originally, the system is marginally stable. Now we are going to turn this into a closed loop system with a proportional controller gain 24 and see whether the system is stable or not. Let me go to my whiteboard. Now this is now a closed loop system with a proportional controller gain 24 selected for us. And all you have to do is obtain the characteristic equation and then obtain the roots to show whether the system is stable or not. All you have to do is obtain the characteristic equation. So that is your characteristic equation. 1 plus GH equals 0 is your characteristic equation. The denominator of the transfer function. All right. So now you want to find the roots of this equation. Okay, so now you obtain the characteristic equation, which is 1 plus GH equals 0. And it turns out it is a third order polynomial. Plus and minus 2.4J. That's correct. JOI. Sometimes some people use J, some people use I for imaginary part of the equation. So normally I use J or I. You can use either J or I. And then there are going to be 3 roots. One real roots at -4, and then there's 2 more roots at 1/2 plus and minus 2.4J. And then you see that there are 2 roots lie on the right-hand side of the imaginary axis, and then we say that this system is now become unstable. Because we have these 2 roots on the right-hand side of the imaginary axis. So all you have to do to know whether the system is stable or not is just determine the roots of the characteristic equation. If there is one positive root, or you have a positive real part of imaginary roots, then you know that the system is unstable. Do you have any question? Why 0? That 0. So the definition of characteristic equation is only then we can talk about the roots of the characteristic equation. So 1 plus GH equals 0 is known as the characteristic equation. The denominator, when we equate that to 0, if we don't equate that to 0, you won't be able to solve for the roots. It is like ax squared plus bx plus c. And then if you don't put equal 0 there, and then it is not an equation that you cannot solve for the roots. That is why we put 0 here. So the definition of this characteristic equation is the denominator of the transfer function equate that to 0. That is known as the characteristic equation. Any other question? Okay, so sometimes we wish that we can have a simpler method of determining whether the system is stable or not. If we are only interested whether the system is stable or not, we don't have to compute the exact root, the exact numerical values of the roots. There are some tests that we can use that we are going to discuss after this. But I think we take a break first. We take a break here. And then we'll come back for, what time is it? It's 4:40. Come back at 5 and we continue from there. Okay, I'll see you back here at 5 and then we discuss how we can determine the stability of the system without computing the exact value of the root. Isn't that working? Isn't that working, taking the denominator? What the hell is going on with my screen? All right, so come back here at 5 and then we continue our discussion.